Now we're going to go one step beyond what we've been doing. We know now how to write formulas, whether they're ionic, covalent, or diatomic. We know how to, based on the type of reaction, how to determine what the products will be, write their formulas, and then balance the entire equation. Now we're going to focus on just the double replacement reactions, which means we're going to have two ionic compounds for reactants. We're going to switch the negative ions places, write the formulas of the products, and balance. But we're going to not only just look at double replacements, we're going to look a little more closely, and we're going to look for just when things change. You can mix chemicals together, and if nothing happens, it's not important. It's like if you mix milk and Kool-Aid together, it may taste disgusting, but it's really nothing's changed. No new chemical has been made. It's just milk and Kool-Aid. And if you look here, we have iron 3 chloride, aqueous, and potassium nitrate, aqueous, mixed together, and it makes potassium chloride and iron 3 nitrate. But if you notice, they're all aqueous. So our iron chloride is disassociated into iron and chloride, and our potassium nitrate is disassociated into the separate potassiums, the three of them, and into the three nitrates. When you mix it all together, nothing's really changed. The iron 3 plus atom is still floating around by itself. The three chlorides, the three potassiums, and the three nitrates are all still floating around. Nothing's changed. This isn't an interesting reaction. It isn't a reaction at all. Nothing happened in this case. So this is an example of a reaction that we're not going to worry about. But when we're looking at double replacement reactions and we want to find when something has happened, there has been a change, this is where we need to understand what the state of matter of all of these ionic compounds are. I'll give you an example. If you look at the video on the right there, it's the mixing of lead 2 nitrate and potassium iodide, two clear liquids. And you see when you mix them together, something has happened. There has been a change. You've formed this yellow solid. So in this reaction, this is an example where we're gonna find out exactly what's changed. We're going to get rid of things that really aren't taking part in the reaction. So if we look at it as particle diagrams, we have lead 2 nitrate. It's aqueous. That means when it's in water, it has dissociated into a lead 2 plus ion and two NO3 negative 1 ions floating around in the water. The two potassium iodides break up, so you have two Ks and two ions floating around. When you mix them together, in this case in the movie in the same test tube, you see that the two Ks don't change and the two nitrates don't change. They were individual potassiums and individual nitrates floating around in the water, and they didn't change. You can see in the reaction up there that the KNO3 on the right side in the products is still aqueous. But what has changed is that the lead 2 plus and the two iodides in the reactants have changed. They've gone from individual ions floating around to being locked together in that solid lead 2 iodide, that yellow substance in the test tube. And that's what's important to us. We're looking at just what has changed. So we're going to take a closer look at that example. Aqueous lead 2 nitrate plus aqueous potassium iodide. The first thing you do when you're doing net ionic equations, you're looking at not the gross complete reaction, but just the net. What has absolutely changed? We're going to dissociate all aqueous ionic compounds because that's exactly what happens to them in water. They dissociate, they break apart. So the lead nitrate is going to break up into one lead 2 plus and two nitrate aqueous ions. The potassium iodide breaks up into the two Ks and two Is. The potassium nitrate on the right-hand side in the products is still two Ks and two nitrates. What we're going to leave alone is that solid lead iodide. It's a solid in water. It's not soluble. I've handed out the solubility flow chart so you can find out what any ionic compound, whether it's soluble or not in water. And lead iodide is not if you go through the flow chart. So our next step is, now that we've broken up all the ionic compounds into their individual ions, that's called the complete or the gross ionic compound, we're going to get rid of things that have not changed from the left to the right, from the reactants to the products. And those are called spectator ions. Okay? If you look at it, the lead has gone from 2 plus to being locked up with the lead iodide. If you look at the nitrates, however, there's 2 nitrates floating around freely on the left, and they're still floating around freely over there in the products, so we're going to cross them out. The 2 potassiums in the reactants are unchanged when you look at the right-hand side of the products, so we need to cross those out also. Those are the spectator ions. They don't take part in the reaction, so we're really not worried about them. So we are going to then just get rid and ignore those spectator ions and be left with what is called the net ionic equation. So it ends up being lead 2 plus aqueous plus 2 iodide negative 1 aqueous produces 1 lead 2 iodide solid. This is our net ionic equation.
Alright, so we're going to talk about net ionic equations, which is actually an extension of double replacement reactions. So let's go into detail on what exactly is happening when you have a double replacement reaction. Okay, so double replacement reaction is when 2 ionic compounds come together and switch partners, right? So typically when you have it is it's in an aqueous solution, meaning that these compounds are in water and making solutions. So let's take, for example, a sodium hydroxide. When you put it in water, it actually breaks up into its ions. We have a sodium ion and a hydroxide ion. The same thing happens with all ionic compounds, but let's reiterate that with copper 2 chloride. Put that in a solution, or in water to make a solution, and we have 1 copper ion, 1 copper plus 2, and 2 chloride ions in the beaker. Okay, great. What does that mean now? Alright, so let's say we added to these 2 beakers together to see what would happen. Well, most of the time you're going to have a precipitate, and a precipitate is a solid form or solid pieces within that solution, so some sort of solid will actually happen. You probably have a solubility chart that your teacher might have given you that tells you what actually makes a precipitate. A simpler way of writing precipitate instead of having to write the whole word is PPT, so you might see that actually in the future too, so this actually means precipitate. These words are pretty important also. Within this reaction, this is going to still be aqueous, and this is going to be our actual precipitate. This is going to be our solid that's going to actually be formed. So we're going to say NaCl, the product, is soluble, meaning it is dissolvable in the solution. It will break up into its ions. It will still be in solution. This is going to be insoluble, meaning that it's going to be the precipitate, meaning it's going to be the solid of this reaction. This is actually going to stay together. So let's write this out more accurately to describe exactly what is happening. So we look at the complete ionic reaction. We're going to break this up. We don't like it together because we know that they separate in solution, as we've mentioned earlier. So instead of writing NaOH, I'm going to write Na plus and OH minus. Okay? Then I'm going to break this up into its ions also, because it's broken up. It's an aqueous solution. So we're going to say it's Cu plus 2 chloride ions. This 2 comes out. We have 2 of these guys, 2 chloride ions. It's going to produce salt, which we said is soluble. It's in an aqueous solution. It's going to be broken up into its ions, Na plus Cl minus. And this is a solid, so it stays together. We're going to say it's CuOH2. Now, I actually forgot to balance the original equation, so we're going to have to go back and make sure this is balanced so we can do it properly. Okay, so there's 2 chloride. Let's go back up here. There's 2 chlorines. There needs to be 2 chlorines here, which means I have 2 sodiums. 2 sodiums there, 2 hydroxides, 2 hydroxides. This is balanced. This will also change our our complete ionic equation. Let's put a 2 here, We have 2 of these guys, both of them. This 2 will tell me I have 2 of these and 2 of these. Okay, so now it's balanced. This is helpful. Okay, so now we have this long equation. This is actually a much more accurate description of what is actually happening in the reaction. Then we go into something called spectator ions. When you think of the word spectator, you might think of like a basketball game. When you watch a basketball game, you're a spectator of that basketball game, right? If you go to like a Wizards game, you would be a spectator at that Wizards game. You wouldn't actually be involved in that Wizards game. You're not affecting the outcome of that Wizards game. You're actually just there watching the event happen. That's what these spectator ions are the exact same way. Okay, they're just watching the reaction take place. They're just spectators. They don't really do anything. They don't affect the outcome of the actual reaction. So what do I mean by that? What's a spectator ion? Okay, well, there are ions on both sides of the reaction. They haven't changed. So for example, we have a sodium ion here and a sodium ion here. That's a spectator. We can actually cross that guy out. He is not doing anything in this reaction. Then we have hydroxide ion. We don't have one over here, so we can't. That's not a spectator. We have copper over here. We don't have copper over here, so that's not a spectator. We have 2 chloride ions, and yet we have 2 chloride ions here. That guy is the same on both sides. He's a spectator. He's just watching the event happen. He's not important. So then we have our leftovers, and that's what we got to get to our net ionic equation, or net ionic reaction. So let me just bring those down. And I'm going to say 2OH minus plus Cu plus 2 gives me CuOH2. Let me make sure this is our solid. This is our net ionic reaction. This is what actually is happening within this reaction. So let's take this and go up and do this one more time, just to make sure that we understand. Okay. An aqueous solution of aluminum chloride and sodium hydroxide react to form solid aluminum hydroxide. All right, let's break this up into its overall reaction. So aluminum chloride, we know this is Al plus 3 and Cl, and this is a minus. So when they actually make their compound, it's going to be AlCl3, and we know it's an aqueous solution, so we're going to write AQ. Okay. Reacts to sodium hydroxide. We have sodium, which we know is Na. This is plus. Hydroxide is OH minus. So together they're just going to be NaOH. And this is an aqueous solution also. React to form a solid, and this tells us what a precipitate is, aluminum hydroxide. So we know aluminum hydroxide is going to come together. This is Al plus 3, OH, and a minus, so it's going to be AlOH3. And then we have another product. So we did the outside one, so we're going to do the inside one. Na and Cl is left over, so we can just say NaCl. And this is our aqueous. This is soluble. Okay, so let's balance this equation, make sure it's balanced correctly. We have 1 aluminum, 3 chlorines. Let's make 3 chlorines here. That makes 3 sodiums. Let's do 3 sodiums on this side, making it 3 hydroxides. 3 hydroxides, good, great, it's balanced. All right, so let's do our complete ionic reaction. We can break it down. Don't forget, aqueous solutions need to be broken down into its ions. Let's do that. We have Al plus 3 plus 3 Cl minus ions plus 3 Na plus ions plus 3 OH minus ions. Yields, this is our solid. We're going to keep this together. AlOH3. And then this is aqueous, so we're going to break that up. Okay, so now we have to find our spectators again. So which ones are our spectators, meaning they're the same on both sides? Well, I have 3 NAs over here and 3 NAs over here. Cross those guys out. 3 chlorides here, 3 chlorides here. Cross those guys out. Now we're left over. This is our net ionic equation. Ta-da, we're done. Al plus 3 plus 3 OH minus yields AlOH3. It's our solid, so precipitate. It's completely balanced. We're looking good. Awesome. The one type of double replacement reaction that you might see, or that you can put into net ionic equation, is what we call a neutralization reaction. This is also a double replacement reaction. The reason we call it neutralization is because we have an acid, our bromic acid, hydrobromic acid, sorry. Then we have sodium hydroxide, which is our base. So together, an acid and a base is going to be neutral, meaning it has a pH of 7. So this is what we call a neutralization reaction. So let's do that. When they trade places, or actually have the reaction occur, the H is going to be now with the OH, so HOH, is another way of, a funny way of writing water, so I'm just going to write water. How many HOH? It's water. And then you have sodium and bromide come together. Okay, so whenever we have water, this is actually a liquid. Water is not aqueous. Water is what's aqueous. It's a liquid solution. Okay, so not a solution. It's just a liquid. It's a liquid state. So this guy, anything that's not aqueous, is going to stay together. Only thing that breaks apart is aqueous. If you have gas, it stays together. If you have liquid, it stays together. Okay, so water is going to stay together. This actually is aqueous. It's going to break up. So let's do it. H plus Br minus. Do we make sure it's balanced? Yeah, it's balanced. Br minus plus Na plus OH minus yields H2O. We're keeping it together because it's a liquid. And NaBr. Na plus and Br minus. We break up, we cross out our spectators. Br is a spectator. Na is a spectator. So we're left with H plus OH minus yields H2O as our final reaction. This is common also. This could totally be Net Ionic Equation and be just fine. Don't forget to include that for liquid. And that's pretty much how you do Net Ionic Equation.